So this is week 2, and we already saw this Chomsky hierarchy of languages. So based on the definition of languages we saw last week, we have mainly three classes of languages: regular languages, context-free grammars, and recursive languages. Where regular languages is completely a subset of context-free grammars, which is completely a subset of recursive languages and some others languages. So this week we will see what DFA is. So DFA is basically a machine model that can that we can use to construct machines for regular languages, and mm, FA means finite automata, meaning these are machines of finite states. So there are some finite states and transitions between them. So the machines we use for regular languages are just finite state machines, and then later we will see that the machine we use for second class of languages, they use a finite state machine plus an additional stack. So you are giving more power to the machine, and Turing machines are the most powerful. Turing machine is basically finite state machines plus some one side infinite length tape. So from top to bottom, the power of machine that we are allowing increases. So the bottommost class of languages can represent more amount of languages, right? That's why everything is a subset of hmm, everything is a subset of its next class language here, right? So we will just look at regular languages and DFS and NFS for the next 2 weeks. Okay. So what are regular languages? So regular languages are basically set of languages for which we can construct these kind of machines. If we can construct an NFA or a DFA for that language, we can just call that language a regular language. But if we cannot call that, but if we cannot construct a DFA or an NFA for that given language, it is probably because it is lying somewhere outside this set in this diagram. So it's maybe a context-free grammar or some recursive language, or that particular language does not have any finite description at all. It's just a not computable language. So we will just have to accept that a regular language is basically a language for which we can construct a DFA or an NFA, basically any finite state machine. Okay. So if a finite state machine exists that can represent that language, we can call it a regular language. Okay. So now let's see what a DFA is. So DFA, it is a machine model, deterministic finite automata, where finite automata basically means it's a finite state machine. It's a machine with a finite set of states with transitions between them, and there is one particular start state and some set of final states. So it is just a machine, a black box machine that represents a particular language L. So that machine takes a string X as input and outputs this. Right? These are what the definition of a computational problem and what's the definition of a machine last week, right? So DFA is a machine model. So we construct different machines, different DFA machines for different languages, different regular languages, and that DFA takes in as input a string X and outputs whether or not that string belongs to that language or not. So that's basically a DFA. So a DFA machine is basically represented by following things. This so it is a finite state machine. So it has to have some finite set of states, which we will call it a Q, the set of all states, and the alphabet set sigma, over which we are defining our language. And one of these finite set of states has to be a starting state, right? We transition between multiple states, but there has to be one start state where we start the machine, and there can be a multiple final states among these whole set of states. So which we used to say like after reading our whole string X, if it ends up in any final state, then we accept that string into the language. The answer will be yes for this. If at the end of reading the whole string, if you end up in a state which is a final state, okay, and then we denote all the transitions between states using delta. Delta is a transition function whose domain is q cross sigma and codomain is q. So this basically means that delta is a two variable function. So delta is a two variable function whose first argument is any particular state q and second argument is any particular symbol in the alphabet set and outputs a particular state. So this basically guides us like after reading a particular symbol when you are at a particular state, which state will you go to? The transition, right? Like for example, assume this state q0. So it has a transition for character 0. It goes to a state q1. So how can we write transition for this mathematically? We can just write delta of q0 comma 0 as q1. Again, like what is a basic thing about function is when you give a function, when you define a function, and if you give a domain, you have to mention what values will the function output for all the values for all the possible values in the domain, right? Like say for example f of x is some normal mathematical function, like like if you say f is a function from set of all real numbers to again set of all real numbers, you have to mention for every real number what is it. Even for a piecewise function like uh, f of x is some just x for f of x is x for all x greater than 0 and minus x for all x less than 0, right? When you mention a function and you give its domain and codomain, you have to mention what that function is for all the values in the domain, right? So when you write a transition function signature like this, you have to mention for all the values in the domain, right? For all q cross e values. Q cross is basically the Cartesian product where you will have where it is a set of all pairs where first element is a initiate q that belongs to q, and second element is some symbol from alphabet. So for every state and alphabet you have to mention to which state it goes in the range, right? For every q comma a, which state does it go? You have to mention for every state in every alphabet, in every symbol from the alphabet. So this is basically your DFA machine. It is a finite state machine with a finite set of states, a given alphabet set, and exactly one start state among these states, and possibly multiple final states among these states, and a transition function where you have exactly one transition to a different state when you are at a particular state and read a symbol. Okay, so let's look at it with an example. So consider this DFA. So this DFA is constructed for a particular language. We don't have to know what language it is currently. So just look at it. Okay. So in every DFA, this is called a transition diagram. Okay. So in this we have three states, Q0, Q1 and Q2. So individual states we can either represent using dots or just circles. Okay. And transitions we denote using these arrows. For reading what symbol it goes to which state in the transition function, we have to mention, right? So for every state you have to mention for every symbol in the alphabet set where does it go. So for Q0 you have to mention for 0 where it goes, for 1 where it goes, right? So for 0 it is staying in Q0, but for 1 it is moving forward to Q1, and also for Q1. For 0 it is going to Q2 using this transition, and for 1 it is going to Q1 with this transition, and Q2 for 0 it is going to Q1 using this transition, and for 1 it is staying in that state only. Okay, so these individual dots or circles, they are basically your states, and these arrows are your transitions, and there is exactly one start state which you represent by a single arrow like this, and set of all final states you can represent by just drawing a circle around every state. So in this case we have only one final state which we represent by drawing a circle around it. So if you write mathematically, you have three states q0, q1, q2. Set of your states as q0, q1, q2, and this is your alphabet set, and this is your start state q0, and your final states is set of only one state q2 in this case, right? And delta your transition function. Write down for every possible state and symbol. So for q0, for seeing a 0, right, it stays in q0, but q0 for seeing character 1, it goes to q1. Similarly these also. And some more things I want to add are like you can, for every state q0, you can write transitions this way. For a sigma 0 comma 1, for 1 you can write two different state q1. For 0 you can write two different state q0. You can also like choose to stay in that state for your machine. So you can also write this way. So this means that if you are at q0 and you read character 1, you will move to q1 state. But if you read a 0, you will stay in q0 state. And you can also write something like this: q0 0 comma 1 q1. This basically means that if you are at q0 and you write either character 0 or character 1 in your input string x, you will move to q1. This is basically 0 or 1. This is just simple way of writing this basically. q0 q1 0 1. Just writing this in a simpler way, you can just write 0 comma 1. Okay. And you can also have this q0 for both 0 comma 1, you can stay there, right? So these are the basic rules for drawing a transition diagram. Every state is represented either using a dot or a circle, and all the transitions over any single symbol for any state, you have to mention transitions for all the symbols for every state, right? For q0 0 where it goes, for 1 where it goes, for q1 for 0 where it goes, for 1 where it goes, for q2 for 0 where it goes, for 1 where it goes. You have to mention every transition, and then you represent your exactly one start state by giving an arrow, and every final state in your DFA you just represent by circling them, right? You can like circle like this, or if you're just drawing circles as states, you can circle over them. So this means that they are final states. Okay. So now let's move to how we can use these. Okay. So as I already mentioned, DFA is a machine model. We can we can construct DFAs for different languages. Like if you construct a DFA machine for some language, say L0. So this is just a machine which takes an input string x and outputs whether x belongs to L or not. Right? So let's see how we can use this machine that takes x and outputs. Okay. So in this case, again we use the same example of a DFA machine. So this is a machine with 3 states and 1 start state and exactly 1 final state. And for every state we have mentioned for every symbol in alphabet set sigma where it goes, right? For 0 and 1 you can find every transition, and this is a DFA that I already constructed, and this represents a particular language. So how we can use this DFA to verify x belongs to L or not? So look at first example. x1 is a string 101. Now we have to use this DFA machine to verify whether x1 belongs to this language L or not. So how we can do that? So you start at the start state Q0 and you keep reading characters in X one by one, and according to the transition rules you move between state to state, and after reading the whole string X, if you end up in one state, you will always end up in some state. If that particular state is a final state, then you accept that X belongs to L. Okay? Again, L is just basically a subset of sigma star, which is any set of strings you can choose. Okay, so let's verify if this string 101 is accepted by the language that is represented by this DFA. Okay, so start at the start state Q0 and read the string from the start. So you are at Q0 and you read character 1, right? So where will you go? For Q0 you have one transition rule. For 1 you will go to Q1. Okay, so now you are at Q2, read the next character in the input string X. So read 0, you are in Q1. So for reading 0 you will go to Q2 using this transition, right? And then you read the final character in the given string 1, and you are at Q2, you read a 1, so you will stay in this state only to Q2 again. So after reading the whole string and traveling between states, you ended up in state Q2, which is actually a final state as we marked before. So since Q2 is a final state, you accept that string into your language. Okay. So similarly, verify this example also. So start at start state Q0 always and read character by character from X. So read 1. Q0 for seeing a 1, it moves to Q1 using this transition. And then for seeing a 0, from Q1 you will move to Q2. And then for reading next one, you will use this transition and stay there. Again for reading another one, you will again stay there. And then for reading next 0, you will use this transition and get back to Q1. And then you read the final character 1, you will use this transition to come to Q0. Right? These are the states that we traveled. So at the end, you ended up in Q0, which is not a final state, right? Only Q2 is your final state. So since you did not end up in a final state after reading the whole string X2, you will reject this string from this language. Okay? So that's how you use DFA machine. A given DFA machine. A DFA is constructed over a single language, right? So every language will have different DFA machines. Okay. So now again let me summarize how to operate this machine. So you start at the start state and read your given input string X character by character. So for every character you go to different state using the transition diagram, right? So after traveling through all the states, when you finished reading the whole string, note down the final state you end up in, and if that state you ended up in is one of the final states, then you accept that into the language. In this case, you did not end up in a final state, so you reject that string from the language. Yeah, so these are the steps. Yeah. So we saw how we can use a DFA to verify if a given string X belongs to that language or not. So now let's see how we can construct different DFAs for different languages. Okay. Okay, so before looking at how we can construct more DFAs that represent particular languages, right? So I can just give me more examples about how to verify a given string belongs to that language represented by the DFA or not. So consider this language. This is some arbitrary language. For this we have already constructed a DFA. I will not reveal exactly what language it is. Let me just tell you again how to use this DFA. Yeah. So verify this string A. Verify if this string is accepted into L0 or not. Okay. So start with the start state. So start with the start state Q0. Read the first character A. So for Q0, for reading A, you will move to second state. Okay. So let's give these names Q1, Q2, Q3. So you have 4 states, out of which one is your start state, one is your final state, and every state you have mentioned transitions for every alphabet A comma B. In this case your alphabet set is A comma B. So how to verify this string belongs to this language or not? So start at the start state and read the first character. You will move to Q1 for reading A. So from Q1 read the second character B. You will move forward to Q2 and then you read the third character A and you move forward to Q3 and then you read fourth character B. From Q3 you will go to Q2 and then read the final character A. You will move to Q3 from Q2. So after reading the whole string, you ended up in Q3, which is one of the final states. In this case, there is only one final state, but since you ended up in a final state, you will accept this string into the language. So also let's look for another example. So look for this string AABB. So again start at the start state Q0. For reading A, it will go to Q1. For reading next A, it will stay there, right? And for reading the next B, you will move forward to Q2 and reading final B. Using this transition, you go to Q0. So after reading the whole string, you ended up in state Q0, which is not one of the final states, right? Final states in this case is just one state Q3, set of one state which is Q3. So you did not end up in a final state, so this string does not belongs to this language this DFA is representing. Okay. So I did not tell you what language this DFA is constructed for. So this is exactly constructed for a particular language, which is basically set of all strings X such that X ends with ABA. So this DFA will output yes for all strings that have this property. Okay. So This is true because this ending with ABA. This is not true because this does not end with ABA. Okay. So this is a machine I already constructed for this language and gave it to you. Now we will see how we can construct our own machines for languages we want. Yeah.